Welcome to the 13th lecture in Abstract Algebra. The topics that we'll explore in this lecture include vector spaces, algebraic structures over the complex numbers, and algebraic structures over the quaternions. Okay, so we'll start this lecture with a formal definition of a vector space. So let F be a field. A vector space over the field F consists of a set V of objects called vectors. The set F, which we call scalars, and two operations called vector addition. Now, vector addition is a binary operation on the set of vectors that takes ordered pairs of vectors and returns a vector. And the second operation is called scalar multiplication. And this is an operation that takes a scalar and a vector and returns a vector such that the set V of vectors under addition is an abelian group. And for every pair of vectors, U and V, in the set V, and for every pair of scalars, A and B, in the underlying field F, the following are true. The set of vectors is closed under scalar multiplication. Scalar multiplication is distributive over vector addition. A sum of scalars distributes over a vector. A product of scalars also distributes over a vector. And the multiplicative identity in the underlying field F as a scalar multiple of a vector leaves that vector unchanged. So notice that in a vector space, there is no notion of multiplication of two vectors, except in the case where the underlying field and the set of vectors are the same, that is, the underlying field and the set of vectors coincide. So let's quickly review how complex numbers came into being. Now, as early as the mid-16th century, mathematicians, and especially algebraists, began to realize that even the simplest polynomial equations did not have a solution in the set of real numbers, which for this lecture we will take for granted that the real numbers is a field under normal addition and normal multiplication. So consider the equation x squared plus 1 equals 0. This equation has no solution in the field of real numbers. That is, there does not exist a real number r such that the square of that real number is equal to -1. And more generally, there does not exist a real number r such that the square of that real number is equal to -a for any positive real number a. And so in order to have a solution for equations of this form, we define the number I so that the square of I is equal to -1. And then the equation x squared plus a equals 0 has the solution set plus or minus the square root of a times I. And numbers of this form were originally called fictitious numbers and later imaginary numbers, and that terminology has remained to this day. Also notice that we can solve more complex equations using this number I. So if we proceed to solve this equation, isolating the variable on one side, we have the quantity x minus a squared is equal to -b squared, or x minus a is equal to plus or minus b times I, so that x is a plus or minus b times I. And numbers of this form were dubbed complex numbers and were considered to have a real part and an imaginary part. And so one of the earliest models of the complex plane was a plane in which we had a real axis and an imaginary axis. And again, a complex number has a real part and an imaginary part. And notice how natural it is to consider these numbers as vectors in a two-dimensional plane. So one of the earliest manifestations of the complex numbers was as the algebraic extension of the reals to include real multiples of the number I. And so this is the set of numbers of the form x plus y times I, where x and y are real numbers, and the number I is the number such that its square is equal to -1. So if we consider this set as a set of vectors, we can now show that this set is a vector space over the field of real numbers. So we define addition of these vectors this way: x sub 1 plus y sub 1 times I plus x sub 2 plus y sub 2 times I is the number x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times I. Notice that we are adding the real parts and the imaginary parts, and so we can think of the sum of these vectors as adding the components, the real and imaginary components. And a scalar multiple of such a number multiplies each component in the vector. So we have a notion of vector addition and scalar multiplication for this set. So we will now proceed to show that it is a vector space over the set of reals. So let z sub 1 and z sub 2 be numbers in this set of vectors. Then z1 plus z2 is the sum x sub 1 plus y sub 1 times I plus x sub 2 plus y sub 2 times I, which is the quantity x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times I. That is z sub 1 plus z sub 2 is x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times I. This is the same as x sub 2 plus x sub 1 plus y sub 2, the quantity y sub 2 plus y sub 1 times I, which is z sub 2 plus z sub 1. And so addition is both closed and commutative over this set of vectors. And notice very clearly this sum is of the correct form. We have a real part and an imaginary part, where the sum x2 plus x1, or equivalently x1 plus x2, is a real number, as is the sum y sub 1 plus y sub 2, or equivalently y sub 2 plus y sub 1. So next we will show that addition is associative. So let z sub 1, z sub 2, and z sub 3 be numbers in the algebraic extension of the reals to include real multiples of the number I. Then the quantity, or z1 plus the quantity, z2 plus z3 is x sub 1 plus y sub 1 times I plus the quantity, x sub 2 plus x sub 3 plus the quantity y sub 2 plus y sub 3 times I. This is the same as x sub 1 plus x sub 2 plus x sub 3 plus the quantity y sub 1 plus y sub 2 plus y sub 3 times I. And so this is the same as the quantity x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times I plus x sub 3 plus y sub 3 times I. And this is the quantity z sub 1 plus z sub 2 plus z sub 3. And so addition is associative over this set. Now there exists the number 0 plus 0 times I in the set, such that for every number z in this set, we have 0 plus 0 I plus the number z is 0 plus 0 times I plus x plus y times I, which is 0 plus x plus the quantity 0 plus y times I, which is the same as x plus 0 plus the quantity y plus 0 times I, which is x plus y times I, which is the number z. And so we have that the 0, or the additive identity, plus z is the same as z plus 0, which is z, where this number 0 has the form 0 plus 0 times I in the set R of I. And for every number z in this set, there exists the negative of that z also in the set, such that z plus the negative of z is x plus y times I plus negative x plus negative y times I, which is x minus x plus the quantity y minus y times I. This is the same as negative x plus plus the quantity, negative y plus y times I, which is 0 plus 0 times I, which is the additive identity. And so we have that z plus 0, correction, z plus the negative of z is the same as the negative of z plus z, which is the identity. And so every element z in this set has an additive inverse. And thus the set under addition is an abelian group. So let A and B be elements in the underlying field of real numbers, and let z sub 1 and z sub 2 be elements in the set of vectors. Then A times z sub 1 is A times x sub 1 plus y sub 1 times I, which is A times x sub 1 plus A times y sub 1 times I. This is a number of the proper form, and so A times z sub 1 is in this set of vectors. And so the set of vectors is closed under scalar multiplication. Now, the scalar A times z sub 1 plus z sub 2 is the scalar A times x sub 1 plus x sub 2 plus the quantity y sub 1 plus y sub 2 times I. This is A times the quantity x sub 1 plus x sub 2 plus A times the quantity y sub 1 plus y sub 2 times I, which gives us A times x sub 1 plus A times x sub 2 plus A times y sub 1 times I plus A times y sub 2 times I. And this is A times x sub 1 plus A times y sub 1 times I plus A times x sub 2 plus A times y sub 2 times I, which is A times z sub 1 plus A times z sub 2. Now the sum of scalars A plus B times the vector z sub 1 is A plus B times the number x sub 1 plus y sub 1 times I. So this is the scalar A plus B times x sub 1 plus the scalar A plus B times y sub 1 times I. And this is A times x sub 1 plus B times x sub 1 plus A times y sub 1 times I plus B times y sub 1 times I. And this is the same as A times x sub 1 plus A times y sub 1 times I plus B times x sub 1 plus B times y sub 1 times I. So this is the same as A times z sub 1 plus B times z sub 1. So now we look at the product of scalars, A times B times the vector z sub 1. This is A times B times x sub 1 plus y sub 1 times I, which is A times B times x sub 1 plus A times B times y sub 1 times I. We can factor out the A so that we have A times the quantity, B times x sub 1 plus B times y sub 1 times I, and this is A times B times z sub 1. And there exists the multiplicative identity 1 in the set of reals, such that for every vector z, we have that 1 times z is 1 times x plus y times I, which is 1 times x plus 1 times y times I, which is x plus y times I, which is the number z. And therefore, the algebraic extension of the reals to include real multiples of the number I is a vector space over the field of real numbers.